live now.
Okay, so do I have to start the talk?
Yeah. You can start, or I can start. I can start. If you want, you can start. I can also start, but we can just talk about anything as we wait for people. Because as of now,
Okay.
we have zero. I'm sure people are waiting. Maybe some of them left because of the issues I had on my side.
Of the delay or problems?
Yeah, delays on my side, but I'm sure they come back.
Okay.
Yeah, but
So,
I don't know if you had seen. Had you seen the title of the stream?
yeah, it was strange for me because uh, by chance I also work in retina implant with a nice guy at Institut de la Vision in Paris. So I can speak also
Yeah.
about retina implant, but it's completely different than brain-computer interface. Nothing to do. I will explain at the end the differences between uh, brain brain implant and retina implant. You cannot use a brain computer interface to
Yeah.
restore vision. It's completely different. I will explain why
Oh,
at the end. But by chance, I know this kind of stuff.
yeah. Elon Musk had said that they'll be able to use. I see they'll be able to use the neural link to be able to restore vision,
No, I disagree completely. No,
and
no,
they said by the end of this year, by
no,
the end of 2025. Huh?
no, no.
And there's also an article I saw recently. I wanted to share with you, but I think I
Okay,
lost it.
okay, but no,
I tried
I know a
I
little
tried to
bit.
get
No. You will
I
see
tried to
what they are doing. No, I disagree completely. I disagree
You
completely.
don't think that they can be able to restore vision in 2025? Although sometimes they say that Elon Musk is known for over promising,
No.
but he said by the end of 2025. So I see we only have three people around. But if you're around, man, thanks for joining, and you can click the like button to recommend us to more people. Do you want to begin with your talk, or we can continue talking about some light
Okay,
things?
I can start the talk.
Yeah,
So you can see my introduction. So I will explain why I am entitled to talk about Neuralink and brain-computer interface.
yeah,
Because I used to work with Professor Benabid. You will see what kind of work he was doing. He was inventor or discoverer of the treatment of Parkinson disease using deep brain stimulation in collaboration with an American company called Medtronics, which is well known in implantable device. And I've also been working on implantable micropump, just test with pigs to treat a special, very special brain cancer, which is very, very difficult to treat, which is called glioblastoma. It's a very invasive. Imagine that the cancers start with a small part in the brain and then
yeah.
goes everywhere in your brain. So you are destroyed in few months. So I work also on this topic, and I was in charge of the development. So I know physics and also image processing and something like this, but I was really in the development. So I met with an industrial partner. We discussed about project and all kind of stuff on pacemaker with a French company. And with them, we were working on vagus nerve recording. You see on the left uh, part of the slide, you see that we were using micro-technology to develop dedicated electrodes for vagus nerve. Vagus nerve is a nerve like this somewhere, and it carries a very large amount of information from the tongue, from the all kind of things from and back to the brain. So it's very complicated to be able to grasp information from this thing. And you see, so sorry for people which are which are not pleased with blood, but you will see some images. Perhaps Chris, you have already seen the images, some disgusting images about implantable devices. And also, I work with Professor Benabid about brain-computer interface. I will explain what we have done with him. And I have had the chance to go to one of the largest neuroscience event, which is called Neuroscience, and it was held in San Francisco, Atlanta, other kind of thing. So first, I will recall some basic information about the brain. Everybody knows that there are gray matter at the outside and white matter. Uh, Approximately 40% of the brain consists of gray matter, and
Yeah.
this gray matter is a neuronal cells body with dendrites. We will see what is dendrites. You have to know that there are neurons inside the brain and also supporting cells, which are called glial cells. So the brain is very soft. I work with Professor Benabid with the, the, the brain of a pig, and I was able to touch a little bit. It's very, very smooth. It's difficult to cut. It's very strange material. It's a very, very strange thing.
You're saying you've touched the brain before.
No, this is the first time with Ben Abid that I touch a brain, but it
Ah,
was an excised brain from
a
uh,
pig.
a pig. A pig, yeah, yeah, because we're working on this implantable micropump, and we wanted to make some measurements, and so he prepared for us a small brain of. I, I have seen a, a complete
You
head when I was working in 3D imaging system, but it was not the brain; it was a human head, which is a little bit scary for
a
everybody.
complete a complete human head
Yeah, yeah,
from your head
a truncated head. Yeah, yeah,
of somebody.
and I go to the hospital for X-ray imaging to bring back hands and legs and all kind of stuff, and then I bring them back because I don't want to carry this kind of thing. I've got a paper in order to be able to carry, but if I've
Yeah.
got a trouble with police, I can show the paper that I am allowed to bring pieces of human in my car. So there are some regulation about bringing human parts in your car.
So,
Okay, so
like you are going to try to implant the brain computer interface or the brain interface computer on the brain of a dead person, or why were you carrying it around?
excuse me, I don't catch your question.
You are saying that you are carrying the head of a person who had died.
The head in the head of the brain. No, I don't.
You are carrying the head of a person who had died.
No, no, we are not working on that people with brain computer interface. We need to work with living humans. There is no
Oh,
interest to just yes, you are right. Your question is good because we have to make some neurotoxicity test. So before introducing something in the brain, you have to pile up a lot of paper demonstrating that your implant is safe. So there are processes in order to demonstrate that your system is safe. So sometimes we may implant into part of the body of animals mainly, but I don't remember that we use directly human tissues for this kind of thing. Okay, let's go on. So the most important part is the structure of the brain. So the brain is a very complex structure. You will see the number, and it has its own immune system because you have to know that the brain is protected by a dedicated membrane that isolate a little bit the vasculature from the brain. So it's very difficult to introduce drugs in the sense of to cure something inside the brain. It's very complicated. You have to enlarge some channels. You have to do some very tricky things in order to treat this problem. This is the reason why when you got brain cancer,
yeah,
it's sometimes very difficult. Okay, so
yeah.
the system is inside. a kind of membrane with a liquid, and it moves. You have to remember when we will be talking about implant that the brain is mobile inside the skull. Is not fixed. Okay, it can move.
The
So
brain.
if you have an implant which is really rigid,
Yeah.
you will got trouble with this kind of things. It's very
You,
important to note. Okay,
you mean
so
the brain moves around, is not fixed at like
no,
a single
it's not
position.
fixed. It can move a little bit, not too far away because you will be hurt by the skull, but it can move a little bit. And this is the reason why you will see that some design use flexible electrode and wires on something like this. We
Yeah.
prefer flexible things. Some people have tried to use silk with deposition of metal in order to be able to move to follow the motion of the brain. So it's a problem. I don't go in details about. You can read everything. One thing which is important is the skull, the bone protects the brain, but there are membranes, a lot of membranes. You see the name, and one is very important is dura mater. So you will perhaps heard about epidural sensor, which means that you drill a hole. You will see how you drill a hole in of the on the skull, and then
Yeah.
you peel a little bit this membrane, and you put a sensor directly onto the tissue, and you see the blood vessel. It's a little bit complicated. You have to be very careful in doing this kind of things. Okay.
I see.
Okay, one thing which is really important is the structure, the big picture of the brain. You see here a kind of picture about frontal lobe, parietal lobe, occipital, temporal. This part of the brain are
Yeah.
mainly dedicated to functions. You see what kind of functions. And for example, when I was working in 3D imaging system, I
Yeah.
work with a neurosurgeon in Rennes, which is in Brittany, in France, and he was treating a young boy which has epilepsy seizure, and with MRI, he found that the epilepsy took place in the frontal lobe. So he decided to cut the size of a mandarin from the brain of the little guy. And by a kind of miracle,
Yeah.
nothing happened after because as the brain is very complicated computer, it can reorder functions. So as the brain and the physiology knows that this part, the part which is on the left with the pink color, the extreme part was not properly functioning, the brain reattributed function outside. So the little boy was nice after extracting something of the size from his brain. Okay, so you have to figure out that the brain what it possesses what we call plasticity. So if you have one part of the brain which is destroyed by some reason, as long as the brain has the time to reorder everything, you will be fine. And I saw an X-ray image of a man, or I don't remember if it was a man, with half the brain. So you see the picture, and
Yeah.
it's impossible. You see just half the brain. The other was full of liquid, and the guy was not so bad. It has half of it. Perhaps you can see the picture on internet. It has only half of his brain functioning. The other part was absolutely empty, and nobody knows how it works. But the guy was not so bad with half of his brain. So there are some miracles. I cannot use another word than miracles. It's nobody can explain something. You will see that nobody can explain a lot of things in the brain system. Okay, so you have a big picture. So you can see also. Oh, sorry. You can. Uh, Uh, yes, you can see also there are what we call ventricles, which is a part with liquid in the middle of the brain. We have a complicated structure. Hippocampus is very important for memory. Hippocampus is the way where the memory is established, and nobody knows exactly how it works, but uh,
So
hippocampus is related to memory functions. Okay.
if they put that interface, where do they usually connect it on the part of the brain?
Okay, it depends
That
on the function you want to restore. If you want to restore motion control, you have to go to a dedicated. I don't. We will see the name. Frontal lobe, decision making movement. Frontal lobe. It's somewhere in the frontal lobe. You have atlases where are mainly located the functions, and you can put the electrode in this part that control motion. Okay, if someone has been his spinal cord cut by a knife or other accident, you have to figure out where is located his frontal lobe and the part which is relative to motion control, and you implant the electrode. If this is a problem of speaking, you have to find another part. It depends what kind of thing. And if we talk about vision, it's
yeah.
completely different because you, perhaps you don't know, the eye does not transmit an image. Okay, it does not retina produces an image, but there is a small local computing power inside the retina, and the
Yeah.
retina connected to the nerve, the visual nerve, and there is a encoding, and when you grab the information from this encoding, you see that the retina transmits information about verticals, about diagonals, about all kind of stuff, but not a complete image. There is not a complete image sent from the retina to the brain, and after the brain will interpret this all this coding. It's a complicated coding in order to figure out what you are doing. So it's very, very different from other function because it's a long evolution from animals, and we will talk at the end about the work we have done with Institut de la Vision in Paris. Okay, so now we have located the function you want to restore, just a few numbers. You see neurons and the dendrites, and you see that on the right that the brain is a mixed between electrical function and chemical function. Okay, this is the reason why most of the drug, like cocaine or something, apply information, apply tricks in the chemical function. For example, there are neurotransmitters that flash somewhere in your brain, and when you take cocaine, there is a kind of discharge of some neurotransmitters. This is the reason why you seem to be Superman when you take some kind of drug. You are very strong. You can compete with everyone, but after the neurotransmitter is missing, so you are down, and so you take another drug to go up, and then you go down, then you go up, and then you go down. So this is a chemical problem. Cocaine and other drugs are related to chemical reaction inside the brain. So one thing which is very important is numbers. In the human brain, there are around 86 billions of neurons. Okay, it's
Yeah.
difficult to figure out, but the most important thing is that these billions of neurons form 100 trillions of connection. You imagine that you have small parts and a lot of connection going to other parts. Okay, so this is 100 trillions of connection. Okay, so people are now working on what we call connectome. This is a kind of map of neurons and all the connection. Okay, so imagine how long it will take to describe for human brain 86 billion neurons connected by 100 trillions of connections. Actually, the best thing that people have done is it's a kind of roadmap. It's a kind of map of all the connection. Okay, so actually they have decoded the connectome of worms, a small worms, and they are working on the rat. Okay, they are working on insects because the brain of insect is not complicated. And the next step is a rat, because it seems that rat and human have something in common. But imagine the time that we will need to figure out how these billions of neurons are connected through trillions, hundreds of trillions of wires. Okay, and you need, in order to really understand how the brain is working, you need this map. Okay, you need to know where the wires are connected. How can we decide? I have a discussion when I was teaching in Vietnam with a friend which is dedicated, which is an expert in microtechnology, and we have a complete different vision. I told him, "Oh, the car, the as you say, not automatic, the self-running car will be ready in 10 years." And he told me, "Oh, the brain will be decoded in 10 years."
Yeah.
I said no. We will take half a century to decode this amount of information. And at reverse, he told me, "You are wrong with the self-running car. It will take a long, a long time because of the power needed, the artificial intelligence." So we were on two completely different levels about complexity of things. But I guarantee that it will take more than 10 years to decode this connection. Okay.
Yeah,
So,
like
and the size, also the
that.
size. Remember the size of the neuron, between 4 to 100 micrometers in diameter. So you have uh, to to design very small electrodes in order to connect to these neurons. Okay.
Yeah,
One thing which is really important is that brain does not feel the pain. It's strange. It's very strange for everybody, because when you have pain, you follow the pain in your brain. But you see here a picture of a man playing guitar, and he was under neurosurgery, and no problem for him. And Professor Benabin explains the same thing with patients uh, with Parkinson disease. There is no problem to make neurosurgery with awake patient, because the brain does not feel pain. Okay, it's clear.
the brain doesn't feel any pain.
No, no. The body transmits information to the brain, so you feel the pain when you pinch your legs or your fingers. But the brain by itself, you can cut part of the brain
Yeah.
without any problem. Do you remember a
Like,
movie, Hannibal Lecter? It's the second movie of Hannibal Lecter. A guy,
no, no, no.
one of the actor has his brain open, and Hannibal Lecter pick up pieces of his brain and take a pan and fry the brain and give the fried brain to the people. Okay, and it's really possible. You can extract part of the brain without any problem. It's absolutely right. Okay, it's important to know that. Uh, why is he playing guitar? I will explain why. Because when you are doing neurosurgery, every brain is different. So when you are touching the brain in order to cut something or to simulate something, it's not clear what you are doing. So it's very important that the main function of the brain continue to work. So The guy is playing guitar to be sure that the neurosurgeon is not destroying cells associated with motion, with control, with music, or something like this. This is the reason why he plays guitar in this nice example. Okay, so the first thing that we can do is to use magnetoencephalography. So, as the name suggests, magnetoencephalography is a way to record magnetic activity of the brain, because you have a small, very small current flowing between neurons, and this small current produce magnetic field. And if you have sensor, very sensitive sensor of this magnetic field, you can make a map of the activity of the brain based on the current circulation. Okay, but you have to properly read that it is written here. The level of magnetism is 10 femtotesla, which means 10 to minus 15. Okay, compared to other signal, for example, the Earth ambient noise is 100 is no sorry, there is another, the next is, yeah, okay, this is here. Okay, so you have to protect all the equipment from other perturbation, magnetic perturbation. And you see here an example of oh, I made a small mistake. This is functional magnetic. Yeah, there is an error. Yeah, here is, you have to go to the next slide. Sorry, I made a mistake
Yeah,
about the
yeah.
order of the slide. You go to the next slide, please.
Okay, we before I go to it, you have point saying that haven't you
I
had
will go
couple
back
of
to
Kenyans made a brain?
functional magnetic resonance imaging. It's better to concentrate on
So
mag. Okay, so skip this
I'm
slide
going back
and
to
go.
it.
Please go to the
I'm
other
going
one.
back to it. I'm going back to it. Before I go back to it, there is a comment from Pona. Um,
Okay,
you're
go.
saying the next Pona, what you're talking about? What you're talking about? Those guys. I told them we were supposed to meet with them yesterday, but they did not pick my call. I'm not sure about their thing if it works or not. But we were supposed to meet with them, but they refused.
Okay,
They did not pick my call. Every time I call them, they say that they are on hold and doing some repairs.
okay.
But
So
I think, yeah, go on then.
okay, so remember, the magnetic field produced by one neuron is in the range of femto Tesla. Okay, but the Earth magnetic field is around 50 micro Tesla, which is 10 to the eighth higher than the brain signal. Okay,
And
so the noise has to be reduced. You will see how, and you are not able with a magnetoencephalography system. You are not able to see the action of only one neuron. You have to count on 50,000 neurons in order to be able to have a tractable signal. It's very important. And this machine costs 2 million euros or dollars, perhaps $2 million. And the cost is higher because, as you see in the picture, you have to protect by a magnetic shielding, which is a dedicated material that filter the ambient magnetic field, and it costs half a million to bring this components. It's called mu metal. I don't know exactly in English, but it's usually people uh, call them mu metal. It was exactly the same material in the whole oscilloscope with tube. Okay, perhaps you have already dismantled an whole oscilloscope, and you see a kind of metal surrounding the tube, and it was mu metal. It's very sensitive to shock. You don't have to to use shock on this metal, because you will lose magnetic properties if you give a shock to this material. It's very, and also there is a kind of Faraday cage to protect from electrical field. So it's very complicated to have this kind of machine. Okay, very very
Yeah.
complicated, and cost. The cost is very. And you see a guy with the head inside of the magnetics, and the sensor are squids, which means this is extremely sensitive magnetic system. For example, a friend of mine, which was working in the mountain to make very fine measurements in the, he developed a magnetosensor, and he explained me that the house where he was, the lab, was only made of wood without any metal. And if you go to the real sensitivity of the squid system, you can see that there is always magnetic properties of wood. Okay, so he selects the right wood in order to reduce the magnetic properties. So, with this kind of sensor, femto Tesla, I don't know if you can imagine what is femto Tesla, but everything was very difficult to handle. So this is the reason why the price of the sensor is so huge, and the room also cost a lot of money to be prepared. Okay, so I made an error. So if we go back to functional magnetic resonance, I made a mix between both. So if you can go back to the slide number 10.
And there's no way like we can just talk freely without the slides.
Okay, okay. So, functional magnetic resonance imaging is a dedicated function inside the magnetic resonance system. And the difference is that instead of making anatomic images, you